Hello and welcome to Better Geology. I'm Andrew Dunning, and I'm here at one of my favorite beaches in Oregon, Short Sands Beach, part of Oswald West State Park. Short Sands Beach is formed at the eastern end of a small cove formed between the rocky headlands of Cape Falcon to the north and Neakini Mountain to the south. These rocky headlands are held up by hard basaltic rock, and the cove is carved into a softer marine sedimentary rock. These mudstones and sandstones erode more easily from the power of the Pacific Ocean, causing this to erode into a small cove. These marine sedimentary rocks date to about 20 to 17 million years ago, when this was part of the delta of the ancient Columbia River. Nowadays, the Columbia River enters the Pacific Ocean at Astoria to the north, but in the Oligocene and Miocene epochs, the Columbia River drained out further to the south, and a wide delta of soft sandstones and mudstones covered this part of the Oregon coast. Over time, these marine sediments have been uplifted and form the basis of the Coast Range and much of the rocks along the Oregon coast. However, starting about 16 million years ago, large bodies of basaltic lava flowed into the ocean here. These basaltic lava flows came from all the way at the eastern Oregon border with Idaho and Washington in the Blue Mountains, where the Columbia River basalt group erupted over a period of 6 million years, sending thousands of cubic miles of basaltic lava across the landscape, down that ancient Columbia River course, and into the Pacific Ocean. This heavy, hot basaltic lava flowed easily into the soft and unconsolidated marine sediments, and this allowed the basalt to intrude the layers of these soft rocks and inflate like a balloon. These are called sills, or planar lateral intrusions of magma. The sandstones and mudstones here are also rich in fossils, including worms and mollusks and all sorts of shallow marine life, which indicates this was a thriving ecosystem some 17 to 20 million years ago. By looking at these outcrops, we know that the basalt came after the sedimentary rocks because, for example, pieces of the sandstone are trapped in the basaltic rock. Additionally, the faults and fractures that formed when these basalts intruded the rock tell us a clear structural history of the deformation of this rock. For instance, fossils are even broken and faulted along these fractures. In some of the areas where these fractures and faults have really disturbed the rock and broken it up, the waves have carved these caves. Some of these are quite big, but importantly, they show the structure of fault zones. How they appear in this rock. Like there's a whole wide area here of fractured rock, but the displacement, the actual motion is concentrated on one plane right over here. And it's along that plane that this cave extends maybe 40 feet back into the cliffside. The rock is a little darker over here. It's got a little bit higher of a silt, kind of a mud content. And I can also see that it's been deformed a bit more. That's probably because we're getting closer to that basaltic intrusion as you get both further toward the ocean and deeper into the hillside. Over the last 16 million years, regional tectonic forces have uplifted the basalts and the sedimentary rocks to form the jagged coastline we have today. Up here at the north end of Short Sands Beach are where the sedimentary rocks are best exposed. Their steep dip toward the southwest reflects the angle along which these rocks were uplifted, folded, and broken as that basaltic magma intruded into them. It is in these thinly bedded mudstones and sandstones that most of the fossils here in the area are found. Here on these outcrops of the sandstones and mudstones here are a series of fossils, including this large example here. This is a type of worm that would have come out of a burrow somewhere over here, reached its tendril out, and scraped back along these sort of fan blade looking features. There's a whole bunch of these on this outcrop along with smaller other worm burrow type fossils like right there. But the reason I like this one so much is because of these fractures cutting right across it. That shows us that these fractures happened after the rock was already solidified and, well, turned into rock. The fractures that are all over this outcrop and a lot of the other rocks around here are indicative of not only tectonic forcing that causes regional breakage of the rock, but also from local breakage of the rock from the intrusion of those large basaltic sills. As those sills inflated like a water balloon, they fractured the rock around it into these sets of fractures that are in places rather evenly spaced and crossing each other at 70-degree angles, mostly. These fractures tell us the main directions of strain, and that indicates further whether the fracture was from the intrusion of the basalt or broader regional scale tectonic forces. The bedding that is clearly visible in these rocks is reflective of something called a turbidite sequence. This is a series of underwater landslides, effectively, of silt and sand that build up these layers of coarse material and fine material over long periods of time. These types of turbidite sequences are relatively common in deltaic systems, like this was being deposited in from the ancient Columbia River. Also most visible at this end of the beach are the landslides that help enlarge and erode this cove. Every few years, a large landslide will slide down these soft rocks and make the cove a little bit bigger. The wave energy of the Pacific Ocean crashing headlong into this soft rock erodes away at the base of these over-steepened slopes, causing them to fail and generate landslides, which deposit rocks, debris, and more sand onto the beach. This has been Better Geology. I'm Andrew Dunning. Thank you for watching.